So arenes are another class of organic compounds that contain the benzene ring. So C6H6 is the benzene ring, and benzene is an aromatic compound. Aromatic means that the electrons can move. When electrons can move along the structure, we say that it's aromatic. And you have double bonds, so it's not made up of single bonds, so it's an unsaturated hydrocarbon. And this is how you represent benzene. So you're going to draw the hexagon here, and then you show a little circle. That little circle shows the aromaticity of benzene. So initially, it was this structure that was proposed for benzene. So C6H6, like this, bonded to each other with alternative double and single bond. And this structure results in an unsymmetrical molecule. Why unsymmetrical? Because you have alternating double and single bonds. But when we study the actual benzene molecule, we find that benzene is a very symmetrical molecule, which means that all the carbon bonds are equivalent to each other. And benzene is also a very stable molecule. Benzene will actually not undergo addition reactions very easily, which means that you will not have something that will add to this carbon. This would disrupt the bonding, the stability of the molecule. Benzene actually usually goes substitution reaction. So where you have that benzene ring is just going to substitute one hydrogen and let's say replace it by chlorine. So benzene typically goes substitution reactions because that ring here is a very stable structure. And that is because of the symmetrical nature of that molecule. Let's see why it's stable in terms of bonding. So when you look at carbon, carbon has 6 electrons. So first orbital, second orbital. And it's going to be involved in bonding. So since we're looking at bonding, we're going to ignore the inner orbital. So we'll look at the second shell, second energy level, and here it can form only 2 bonds. So what will happen, it's going to go in the excited state where you're going to have the unpaired electron. So 1, 2, 3, 4 unpaired electron, therefore it can form 4 bonds. Now when we look at this carbon here, we find that this carbon is forming 1, 2, 3 sigma bonds and then 1 pi bond. So there is 3 sigma bonds and then 1 pi bond. So what happens is that you have these 3 which are used in sigma bonding, and this one here, this is an unhybridized electron. So these 3, they're going to be hybridized. So you have the S and the P and another P. So this is sp2 hybridized sigma bonding. And then there is one electron. This one is unhybridized. And this one unhybridized electron will actually overlap sideways. So you have 6 carbons. Each of these carbon is going to give 1 unhybridized electron. So you end up with 6 electrons which are not used in bonding by each carbon. So these electrons are going to be involved in hybridization. They're going to form, not hybridization, but they are going to form the aromaticity. It's going to form an electron cloud that is going to be delocalized. So these are delocalized electrons. They're not used in bonding. So the hybridization here is sp2 hybrid. These electrons involved in the sigma bonding, and if it's sp2 hybrid, so it's trigonal planar. This is why we say that. So benzene here is planar. It's a planar molecule, and inside here you have that this region of delocalized electron. So in the benzene ring, you have these orbitals. So these orbitals, they contain the delocalized electrons. So these electrons are not involved in any bonding. So it causes an overlapping at the top and an overlapping at the bottom. If you still remember, sigma bonding is head-on overlapping, while pi bonding is sideways overlapping. So here you have the sideways overlapping of these orbitals. So they can overlap like this, or they can overlap like this as well. So whichever way they want to overlap. So there's overlapping on top of the plane, and there's overlapping at the bottom of the plane as well. So you end up with a cloud of electron on the top of the plane and at the bottom of the plane. So all 6 carbons are joined in a ring. The unhybridized 2p orbital, so this one, this unhybridized 2p orbital, is going to be involved in sideways overlapping, forming that pi bond above and below the plane. These 6 electrons are free to move throughout the ring, so they are delocalized electrons. They move around, and this is a very stable arrangement, and it lowers the internal energy of the molecule. So low internal energy means that it's very, very stable. So nothing will want, like the molecule will not want to disrupt this stable delocalization system. So as you can see here, you have the orbitals on top of the plane and the orbitals at the bottom of the plane, and then you have the electrons that can be delocalized both above and below the plane. So you have the pi electrons here. And you have resonance structures for benzene. Resonance structures means that this bond here, this electron involved in that double bond, so these are the pi electrons if you look at, so pi bonding. So this pi bonding, these electrons, because they are delocalized, they are not fixed between these 2 carbons. Because they are delocalized, they can roam around. So it can shift here, shift here, shift here. This is what I was showing here. So it can form between these 2, or it can form between these 2. Okay, so they can shift, and then see the double bond is shifting here. So it's not the same, it's shifting. So eventually, instead of drawing these 2 resonance structure, we draw the resonance hybrid. This is the resonance hybrid that is shown here. And that ring here that we draw is the delocalized pi electrons. Now, what evidence supports this model is the bond length. When we do X-ray crystallography and we find the bond length of the carbon-carbon bond in benzene, we find that it's 0.139 nanometers. If it was a single bond, it's 154 nanometers, 0.154 nanometers. If it's a double bond, it's 0.134 nanometers. But when you look at the bond in benzene, it's 0.139. So it's intermediate between a single bond and a double bond. And actually, the bond order, so bond order is the number of bonds. Put simply, for SL level, bond order is simply the number of bonds. So here, single bond order is 1, double bond order is 2, but for benzene, bond order is in between single bond and double bond order is 1.5, so in between the 2. The second evidence is enthalpy of hydrogenation. When you add hydrogen to cyclohexene, it takes 120 kilojoule of energy. So if benzene contained 3 double bonds, so if you add one mole of hydrogen to a double bond, it's 120 kilojoule. So if benzene had this structure where it had 3 double bonds, so it should take 3 times 120 kilojoules. So it should have been 360 kilojoule per mole to add 3 moles of hydrogen. So if benzene contained 3 double bonds, it would be expected that the enthalpy of hydrogenation would be 3 times as much. However, practically, enthalpy of hydrogenation of benzene is minus 210 kilojoule per mole, which means that it takes only 210 kilojoules per mole to add that hydrogen, which means that benzene is more stable than predicted by the Kekulé structure. So the delocalization of the electron minimizes repulsion between electrons. Benzene is more stable by 150 kilojoules. This energy would be required to overcome the special stability of the delocalized ring. This is called the stabilization energy of benzene. So instead of 360, it takes only 210 kilojoule per mole to hydrogenate benzene, which makes a difference of 150 kilojoules. So this means that benzene is more stable than this structure by 150 kilojoules. Why is it more stable? It's because of that delocalization of electron. So the delocalization will minimize repulsion between the electrons, therefore makes hydrogenation an easier process by 150 kilojoules per mole. So this confirms the stability of benzene and refutes that structure proposed by Kekulé. The third proof is the type of reactivity. So benzene is very reluctant to undergo addition reaction. So if benzene would have this structure, it would easily undergo addition reaction. As you know, if you still remember your IGCSE, alkenes undergo addition reaction. What happens during addition is just that this bond breaks and opens up and you add something else to it. So you can add HCl, for example. But benzene is very reluctant to undergo addition reaction. It would mean that you have to disrupt that cloud. That very stable cloud would have to be disrupted to be able to add 2 atoms over that structure. Therefore, what happens is that benzene does not undergo addition reaction. That structure would be unstable, but it's more likely to undergo substitution reaction. And substitution reaction, so you're just taking away that H and you're replacing it by something else. So you can replace it by CH3, you can replace it by halogens. This is a substitution reaction. And because benzene is a very symmetrical molecule, there is no alternating double bond and single bond. All adjacent positions are equal. So when we're saying 1,2-dibromobenzene, you can write 1,2-dibromobenzene for all these ways. These are not isomers. These are a single molecule, because when you're numbering, when you're counting the carbons, so let's say you have your benzene here. So 1, 2, 3, 4, 5, 6. So then you have your bromine and your bromine here. Or you can count as from here. 1, 2, 3, 4, 5, 6. Or you can start counting here. 1, 2, 3, 4, 5, 6. Or you can start counting here. 1, 2, 3, 4, 5, 6. These are all ways that you can count the carbons. They are all equivalent. There is no dominant carbon in that. And because they are all equivalent, means that there is no, like, you can't say there's 4 isomers of 1,2-dibromobenzene. These are all equivalent structures. So this is the 4th proof that the Kekulé structure here, this is rejected. If that would be the Kekulé structure would be the correct structure, this and and this would be different. If it would be the Kekulé structure, this and this would be different. But they are the same when you consider the benzene actual structure. Okay? So these are the 4 proofs that the Kekulé structure was wrong and that the actual benzene ring has delocalized pi electrons above and below the plane. And with this, we end with 10.1.